be here, and I want to talk about these two pictures. In the upper picture you see molecular dynamics in some sense, and in the lower picture is a simulation of growing dendrites with the stochastic Allan-Kahn equation. So my interest is here is so I'm interested in the question, what is the noise in the stochastic PDE, and what are the flux functions? And maybe I continue here. This is ID 0. ID 0 is to look on the time independent Schrödinger. And from there, in some sense, come to stochastic molecular dynamics, and from stochastic molecular dynamics go to SPDE, and this will be by computation, and this right is by analysis. So this is sort of a naive, of course. It has to come with not only ID 0, it has to be something more. The main idea is to look on the time independent Schrödinger formulated as a Hamiltonian system. That's my main idea, and what I want to try to explain now. Okay, so here we have this. What about molecular dynamics then? Suppose we have particles x that could, in the previous picture here, this is a simulation of phase transition. So it's liquid here and solid here, and the phase transition, and the particle position I call capital X. They solve dynamical system like this with the potential lambda. And one could ask, what is the lambda? That would give an ensemble with constant energy. Suppose you want to simulate it phase transition at constant temperature. Then one could use the Langevin equation where you have the particle position, the acceleration, and the forcing from the potential, and you have a friction term, k times the velocity, and then you have a fluctuation here with Brownian motion and the temperature T. So now one can also ask, what is the friction? This is something I will try to answer, and as I said, I will start from the Schrödinger and then view that as a Hamiltonian system, and introduce Gibbs measures on that Hamiltonian system. And I have two results. So the Schrödinger-Gibbs measure is close to the molecular dynamics Gibbs measure if there is a spectral gap. I will explain later what I mean with spectral gap, but the electrons are in the ground state and the next eigenvalue is far away in some sense. And then there is something about the dynamics, so the time correlation. If there is a spectral gap and we start with electrons initially in a Gibbs distribution, then for finite time the Langevin dynamics approximates the Ehrenfest dynamics, which is a variant of Schrödinger.
Why are you using second order dynamics? Why is inertia important? Why don't you use first order dynamics?
Yeah, so here if you want to study if you just would like to study equilibrium, that I could use only positions. That's right. But if you would like to know something about the correlation in time, also the friction here will be important in some sense. So if you want to compute the diffusion coefficient, you will look on the difference of mean square distance, which you cannot do if you just look on anyway. So let me now.
But you make the assumption that the dynamics is Langevin.
No. So far, I didn't assume. I just know. For which statement did I assume that? You mean?
When you wrote down the Langevin equation.
No, I just wanted to explain what they are.
Transition from Langevin to first order dynamics works just for small mass, and you put mass equal to what?
Now, let me start giving the talk. Is that okay? Here is the Schrödinger equation. It is a fantastic equation because it has everything is known, nothing unknown. Here we have the kinetic energy of the nuclei, and then we have the part involving kinetic energy for electrons and Coulomb interaction between nuclei and electrons. So everything is known here. I denote by small x the electron coordinates and by capital X the nuclei coordinates. And I assume now that the mass is large for the nuclei and the electron mass is 1. Now, so I will review how to derive molecular dynamics in some sense. So the usual step is that you you start with the ansatz of of an eigenfunction of the Schrödinger. So you write it as an amplitude function times an highly oscillatory phase function, which depends only on the nuclei coordinates, and this depends on both. And this is supposed to be real. Okay, now you plug this into, so maybe I write it here. So we have the Schrödinger, and the Hamiltonian is like this. And then we have the WKB. Like that. Okay, so suppose now you plug this into the equation, then then we will get the following. We will get the following. So if I multiply this by phi, the complex conjugate of psi, and integrate over all electron coordinates, then I obtain the following Hamilton-Jacobi equation. So the dot here, the dot means integration with respect to all electron coordinates.
So you interested in asymptotics as massive large?
Yes.
So this asymptotic.
Yes, that is. I'm interested in the asymptotic results with large nuclear mass. So that is for hydrogen at least 2000, and any other molecule larger. Okay. So here we have this, what I wrote on the blackboard. And from this is the starting point for deriving molecular dynamics. So if one will look on the main part here, then one can do another approximation, which is this. I continue to write some things on the blackboard. So if you assume that you have a state, an electron state, the wave function psi is an eigenfunction. And then you plug this into here. Then we obtain the so-called Born-Oppenheimer approximation, that you have a Hamiltonian consisting of kinetic energy and potential energy, and the dynamics of this is this okay, that's the Born-Oppenheimer approximation. Now another approximation is Ehrenfest dynamics, which I write down here. Then I don't assume that we are in an electron eigenfunction state, but I neglect these terms. So a way to write it as a Hamiltonian system is like this. I want to introduce, I want the nuclei to be in slow coordinates and the electrons fast. So I have my kinetic energy for nuclei, and then here is the Hamiltonian. So now, what is the dynamics, the Hamiltonian system for this Hamiltonian? So here you get P, and then you differentiate with respect to X here, you have that here, and then you differentiate with respect to phi, the real part, and the imaginary part, and you can write that as a Schrödinger equation. Now I choose to normalize here, so that this factor here becomes precisely what we have here. So it's a normalized wave function. So what you have here will generate a normalized eigenfunction with this factor. and since this is linear, you can just multiply with any factor here. Okay. I will come back to Ehrenfest dynamics later, so I don't write it now. Now I said that here is my idea. I wrote to write the time-independent Schrödinger as Hamiltonian system. This means I would like to write. So far we did two things. We simplified here and got that, and then we took everything here and obtained a Hamiltonian system. Now I want to include also these terms, and that turns out to be possible also, in fact. So here is that Hamiltonian system. Then we have a function Vs, which has the same part as the Ehrenfest dynamics, and then it has a smaller part here, 1 over m. Okay, and then the factor g is defined is related to the density by a transport equation relating to the phase here, and then the phi is defines another function psi. So what happens is that if I now solve this Hamilton-Jacobi equation, then I generate characteristics by characteristics. So the transport equation turns out to be very special. It is so that this term becomes 0, the transport equation. So this is the, if I write down the next slide, we have the, so if I plug in now my ansatz into the Schrödinger operator, and then as I did here, the same thing. Now then I generate these terms. I just added and subtracted Vs here. Otherwise, no change. Okay. So the first term here is 0 by construction, since it is a Hamiltonian. This is my equation, 0. Then the next thing here, that is actually the same as, is related to my Schrödinger equation here. Because here we have a time derivative, and this by a change integrating factor, everything become a time derivative. And what we have here, this is the function v hat is defined here. Okay, and then the difference comes from just changing, multiplying by an exponential function. So the characteristics here make everything here equal to 0. So this is just formal, but it is useful to have this thinking that you can think of the time-independent Schrödinger as a Hamiltonian system. Okay, so now when I know that, I want to understand what is the noise in molecular dynamics using a Hamiltonian point of view. Okay, so then I go to the Swansea model, and which consists of is a Hamiltonian system with light particles and heavy particles, and this model uses an explicit solution. So the light particles are have a harmonic potential. But the setup is very useful, I mean. So here is the setup. You think of in the particles initially in a Gibbs distribution, the light particles in the Gibbs distribution. Then you look for what is the dynamics of the heavy particles with the light particles having that distribution initially. Okay, then you see that you get the generalized Langevin equation for the heavy particles. Okay. It turns out that with certain assumptions on the frequencies, you can simplify it to a pure Langevin equation. The generalized means that you have an integral kernel instead of a delta mass in the memory. Okay, so with a certain assumption of the coupling and the frequency distribution, you get the pure Langevin. So that Langevin equation has an invariant measure, and it is the same as the one it is the, if you started from a Gibbs distribution, you are still in that Gibbs distribution, but the marginal of that, which is here. I want now to show you how it works, and I have given talks on this topic before, so some of you have heard me talking on this, and when I anyway want to talk about it, so then some of you will hear the same thing, but there are some changes. So I tried to think, can I make something different? I don't know if it's better, at least it is different, but here is a different view. That when I read Swansig's paper again, I thought, it can be very close to the Ehrenfest dynamics. So this is what I want to show you, that the Ehrenfest dynamics is a particular, it's almost the Swansig case. It's not exactly, but almost. So now we will see how close they are. Okay, so the Hamiltonian in the Swansig model consists of the kinetic energy of the nuclei, and so my heavy particles are now the nuclei. And then we have a potential, and then we have an interaction between the heavy and light particles, which here are the coordinates for the light particles. And then we have a function psi here, which is related to the friction. And then we have kinetic energy of the light particles. Whoops, where was my pointer? Yeah. Okay.
So this little m now is the ratio between
this small m is Swansig's m. I put here the capital M is 1 in this case, and this is the mass of the light particles. So capital M is 1. The next slide I will relate them, but this is supposed to be smaller than 1. We will see it soon. Okay, so what happens? If now I introduce psi, which is x minus I times the momentum here, or velocity, and minus this, then the dynamics generated by this Hamiltonian is, here we have the heavy particle dynamics with the potential lambda and the interaction term here. So psi prime is the derivative with respect to x there. And then we have a Schrödinger equation for the light particles. Okay. But so we see already that it has some similarity with the Ehrenfest dynamics. Here we have a Schrödinger equation and then another coupled to another equation. Okay, so suppose now you sample psi initially from the Gibbs distribution. Then they will become independent normal because of the structure here. Okay, and you can explicitly solve, given the capital X, you can explicitly solve for psi. And then you plug this back into here using Duhamel's principle. So that's on the next. This other thing that happened is stuck now. Yeah, here we are. Okay. So what happens now? Now I want to compare this Swansea model with the Ehrenfest dynamics. Okay, so the Ehrenfest dynamics, I write it down. Since we will look on it several times. So here's the Ehrenfest dynamics. And then I have made some changes. What are the changes? I have shifted off the eigenvalue corresponding to the ground state and called a new electron potential V tilde. And then I have shifted the wave functions from the ground state. And the Ehrenfest dynamics I wrote before then becomes this system with a forcing and interaction term here, and then we have a quadratic term, and then we have a Schrödinger equation for the wave function. Now let us compare these two. This was the Swansea model. What do you think? Are they close? Do they look close? If we first look on compare the wave function for the electrons corresponding to this dynamics for the light particles, we can choose this V hat to be equal to that. But here, in order to solve it, Swansea gives a constant potential. I mean harmonic, so it should be constant. I will later not use constant here, but formally it looks similar here and there, very similar. Okay, and then what is the difference between this and that? It's a question to you, to not fall asleep here. Or what's the difference? Here we have something there, and here we have there. What's the difference? I will give you an ice cream, the one who first answered this. But yeah, so the difference is the quadratic part here. There is no quadratic part here. Simple question, a simple answer.
What about M capital?
Yeah, sorry?
What about M capital?
M capital, I can include that here.
Because you assume that M is large.
This is large, yes. But when I define the Swansea West formal model, I can choose n. It was just a set of parameters following his notation. So I just use the notation V hat, but I could call V hat. I could call that V hat could be equal to m1/2 times V tilde, if that would be constant. It's possibility. And then I could choose the capital M to be 1 over square root of small m equal to 1 over square root of capital M. So then these two terms would be the same the same. That is the new thing for this conference. I realized that. Although I thought about the problem for, I don't know, embarrassingly long. So I'm very grateful to come here. That they are so similar. So now, I don't know how much you want to know about details, but I still have some time. So
Isn't the difference really substantial?
yes, I mean there is a difference, of course. Here we assume that v hat was constant, and we did not there. But if they are going to be similar, this term would have to be small in some sense. So we could put in assumptions, and this is what I assumed. If you have a really large spectral gap, this will actually be small. And I will show you precisely what I mean with the large now. And then another difference is that to analyze the Swansea dynamics, you use an explicit solution. I cannot do that because if this is not constant, it depends on x, I cannot solve it explicitly. So there is a difference. And I don't want to make assumption. I mean, I showed you here. Here we find Langevin equation with some assumptions. I don't want to make any assumptions about the frequency distribution, because here, in some sense, you get Langevin, but you don't know what is the friction. You just get something, a parameter. You don't know what the parameter is. Now, I will show you what the parameter is. Let me see. So here is the Swansea solution. Maybe I quickly. This was linear, so you can solve it. You just solve it. Here is the solution. Then you plug it into the equation here for the air, not for the Ehrenfest, but for the Swansea. Then you get a solution, okay, and then you have it. And then you assume certain things about the frequency later on. This is a generalized Langevin. Now, to make it a pure Langevin, this integral kernel has to degenerate to point mass, and that you can do by assumptions on the frequencies. Okay, and it has this property that the integral kernel is equal to the covariance here. Okay, so here is the assumption on frequencies, and then you get the Langevin equation. It's not so important precisely what assumptions you do, but in essence, you get the Langevin equation, but you don't know what is the parameter because you have assumed certain things. I would like to get the precise description, but first maybe I come to this. Now, do we like this model, the Swansea model, or not? Is it good? I like it, but do you like it? Yes. Yeah. Class A and Class B. So suppose it has this nice stability property. If you start with a Gibbs distribution for the electrons initially, then you get nuclei eventually in the marginal of the original distribution you started with. That is great. It is a stability property of the dynamics, which is nice. But suppose now that you start from, so what is particular with the Gibbs measure, I was thinking. When I have given this, tried to explain this before, when you have quantum mechanics, you should maybe take some other distribution for the electrons. Why should you take this classical? I reduced it sort of to classical. Why should you take this classical Gibbs and not read these thick books about quantum fluctuations and complicated distributions? Why not? Yes, so I think to me it looks, you can simplify by looking to the classical. I showed you they are very similar. The dynamics of Schrödinger, it is also like classical. It just, you can rewrite it one way or the other. But what is particular with the Gibbs distribution? One particularity is the stability, that you start with this and then eventually end up in the heavy particle dynamics, which is the same. So suppose you will take another equilibrium measure of the, you have a Hamiltonian dynamics. You could take any other equilibrium measure. Now, and then sample the light particles from that distribution. Okay, what would then happen for the heavy particles? Would they come into the eventually? Would they come into the same equilibrium measure that you started with? Okay, so here is an argument that you may know that, but I didn't. That it's only the Gibbs measure that has this property. That you so here is this argument. So suppose you start with any equilibrium measure and you have a system with large heavy energy compared to the light energy is smaller. And you measure this in the number of particles. So you have more heavy particles than light, or modes if you want. Okay, so now I claim that if the light energy is smaller than the heavy, then it is a good approximation to use initially the Gibbs distribution for the light, although you started with any equilibrium measure. Okay, that's good, because then we can use Swansea dynamics, and you end up with Gibbs for the heavy. If this should now be the same, it should be the same as you started with. So then you have only the possibility of Gibbs. So let me show you now. This is simple, but here are some assumptions. You have the Swansea model, heavy particle Hamiltonian part and light particle Hamiltonians. Okay, and then we assume that you have more energy in the heavy than in the light. So more particles here in the heavy than in the light. And then we take G to be the logarithm of the equilibrium. We take any equilibrium positive, and then we let G be the logarithm. And then we assume certain things about the derivative should be bounded. So if G is a polynomial, for instance, this is satisfied. Suppose we have that. Okay, now we want to look on the what happens when you perturb the equilibrium measure with the light. Then, in fact, the linear approximation is good because of my assumptions. And the linear means that it is a Gibbs. Okay, so that it is okay to sample the light particles from the Gibbs, and then we end up in heavy particles also in the Gibbs distribution. So by consistency, it's good to use Gibbs. So that is my motivation, and it is valid also for electrons. It doesn't talk about if you have Schrödinger or anything. It's okay always. Okay. Now here is again a little bit about the background. Now we have 5 minutes left. So there are two theorems, and maybe I state now. So the first theorem I said was, if you now compare the Schrödinger equilibrium Gibbs state with the molecular dynamics equilibrium state, are they close? Of course they are not in general, but here is an assumption that makes them close. So now you let lambda be you take the temperature T, and then you look on the gap. So the first eigenvalue is called lambda 1, and then you say you normalize them so that the difference of eigenvalues is called lambda bar, and the first one is the gap then, lambda 1 bar. So suppose temperature is smaller than the gap. Okay, and assume then that the derivative of the eigenvalue divided by the eigenvalue also is small when you sum them. Then, in fact, it turns out to be a good approximation. If you let the drift in the Langevin be the ground state potential. One can perturb this with the temperature. So if you assume a little bit less, that instead of having this bounded, having that function bounded where you divide by the square, then you have an approximation if you let the drift include some part of the temperature. So the temperature will affect the potential. It's reasonable in some sense, but here is what is precise. Okay, and I think this will. I go back to this as a high time. Now we take the other. I said with slow time dynamics, the correlation for fixed time. So now, if you want, I want to determine the friction parameter. Okay, and I said I want to use Swanswig setting, but the difference is that instead of having an explicit solution, I would use the fast dynamics of that equation. And there is a nonlinear coupling, which is handled by a large gap. Okay, and would I get the temperature contribution? And my error is now, I don't have an explicit solution. So I look on the Kolmogorov equation for the Langevin equation and study the residual when I put in the Ehrenfest dynamics into that Kolmogorov equation. That measures my residual. Okay, so that's the idea, and here is the result. So if I let the friction be this function, so the friction in the Langevin equation is small, 1 over square root of m, and it depends on these two derivatives. I assume that the gap conditions are the gap is very big. Then, in fact, the Langevin dynamics here approximate the Ehrenfest dynamics with an arrow which is smaller than square root of m. So it sees the friction, for instance. Okay, and then I have to assume that I have used an observable that is smooth enough so that the Langevin dynamics is very smooth. Okay, and then the conditions here are similar to the equilibrium case, that if the derivative of the eigenvalue divided by the eigenvalue, the sum of these is small, then I have the pure eigenstate, the eigenvalue. And if it is slightly weaker condition, then I can get the temperature contribution to the drift. Okay, I think I just want to show you one thing, how to find the friction without assumptions now, only that the capital M is large. So we have the forcing here is here, and the friction term is generated by this function here, depending on the velocity of the heavy particle. Okay, so that comes from solving the Schrödinger equation. The solution operator for the Schrödinger is here S. So the solution operator for this here is called S. Okay, so and that this term here, that generates the friction, and this now sits here. Okay, so this is the friction term. Now you can rewrite it by just differentiating with respect to time. Here you do that. Then you will get by the dynamics square root of m times tilde v. Okay, but now if I divide by that, I have done nothing. Okay, and then I could now integrate this out if I also take a term that compensates that you differentiate here with respect to time. But this is a bounded function, so you take a derivative here, you will just get something order 1. But here I have gained the square root of m. So you get another integral. So if I just integrate this up, I will have this term, which is the friction term. And then I will have a remainder term of an integral of the same type as here, but with a square root of m downstairs. Okay, I stop now. Thank you for listening.
Any question, please?
You estimate 1.
Estimate
Just the previous slide. Sorry. Does the constant depend on time? So it's for finite time interval or?
Yes, this is for finite time.
This is for finite
Because this assumption will be unreasonable if this time would grow, I think. Yeah. So I don't know, maybe you specialists know how to prove this for a long time, but I don't know how to do that.
Other questions? Then let's send the